Hello, everyone. Thank you so much for being a part of the first of the Computation Sustainability Open Graduate Seminar. Today we have with us Ming, who is a postdoctoral scholar at University of California, Berkeley in the Department of Industrial Engineering and Operations Research. And today he'll be talking about trustworthy data analytics for safety critical systems. So without any delay, I'll hand it over to Ming.
All right, cool. Thanks a lot for the introduction. Hello, everyone. I am Ming Jin, and as Harry mentioned, I'm a postdoc at the University of California at Berkeley, and I work on optimization, learning, and control for safety critical systems like power system and buildings. And this talk is really about designing algorithms that are guaranteed and also trustworthy. So if you think about modern learning, a lot of that is about data. We collect a huge amount of data from the new sensing modalities coming out every day about our health, our environment, and also the infrastructures around us. And we want this data to help us make better decisions, improve our way of living, and also enhance the infrastructures around us. And I think part of the reason this is happening is that algorithms have really succeeded. In the realm of artificial intelligence, whatever that means, we see tremendous advancements in areas like image recognition, natural language processing, and game playing, to the extent of matching and even surpassing human level performance. And this all gets people excited, and a lot of public media touted data as the new oil and AI as the new electricity. And probably brought together, they will solve pressing issues of the societies. But as exciting as it is, people also quickly found that a lot of the systems and algorithms that we have are kind of brittle. For example, you could manipulate the image in an imperceptible way to completely fool the classifier. That's well known as the adversarial examples. And this goes well beyond computer vision to speech recognition, where you could create inaudible noise to fool Alexa, and the reinforcement learning, where you could behave randomly and uncoordinatedly in order to gain an advantage of the victim. So adversarial robustness is sort of something that we already know, but is still caught us off guard. And I think it behooves us to stop for a moment and think, okay, is the technology, the way it is now, truly ready for real world deployment? Because when it comes to the real world, like power system, buildings, or autonomous cars, they are all very different from each other and challenging in their own ways. But one thing they have in common is that they are all safety critical with people involved. So we care about the reliability of our algorithms, and we care about the safety of these systems. For example, power system is probably the most expensive and large-scale machines that people have ever built on Earth. Yeah, so power system is probably the most large-scale and complex engineering systems where electricity generates, distributes, and transports to millions of homes. And when it comes to the operation of power systems, there are entities like ISOs and TSOs that are performing serious operational problems. Problems from discrete optimization, like unit commitment, to continuous optimization, like optimal power flow and state estimation. These are all serious optimization problems and challenging in their own ways, but one thing that they have in common is nonlinearity. According to the federal agencies, the annual cost of doing approximation due to nonlinearity is way over $1 billion per year. And on the other hand, a single fault and a blackout could seriously set back the economy and affect people's living. So to address these issues, the general goal of my research is to develop computational algorithms with formal guarantees of performance. And in many of these cases, the design of the algorithms can be converted to an optimization problem. Now for our optimization, we want to minimize an objective function fx subject to a bunch of constraints on x. And no matter where you look and what applications that you are working on, there will be several universal challenges. The first challenge is nonlinearity. because a lot of the real world systems like power system or transportation, they are highly nonlinear. And also our controller could be nonlinear. So because of that, the optimization landscape could be quite complicated. And even finding the global optimum is not easy. And another challenge is that we are dealing with untrusted data. The adversarial examples that I showed you before might look like an artifact, but when it comes to the real world, we are actually getting data from everywhere. They could be noisy, uncertain, corrupted, and adversarial, and they could be of different types and provenances. So we no longer have fine-grained control over what we get. So even forming the optimization would be a challenge. And most importantly, we have an issue of scalability. On the one hand, we have urban systems like power system becoming increasingly large scale and complex, coupled with millions of devices and human interactions. So we really need to make decisions fast. How can we make real-time optimization, real-time control, real-time learning? On the other hand, when it comes to people, we are often dealing with limited data. So how can we learn efficiently in the low data regime? So my sort of general interest is to develop trustworthy data analytics because, as I alluded to earlier, current methods have serious trust issues. And towards this end, I have worked on a variety of projects that can be generally grouped into two directions. The first direction is on computation, where the focus is on physical intelligent systems. The research question that we study there is what is the attackability of the system and how can we come up with potential defense mechanisms. So compared to adversarial machine learning, where the primary focus has been on deep learning with structured data like images and text, here we are considering a broader set of robustness problems arising from the control and optimization problems in physical systems. And this will also be the main part of today's talk. On the other hand, when it comes to operations, we also need to consider the human factors. So in the second direction, I design algorithms that incorporate the human factor into the system operation. The challenge is that we are often dealing with limited data when it comes to people. So I designed a bucket of techniques to address this issue in the low data regime. And this line of work have received 3 Best Paper awards and also has been featured in some public media like IEEE Spectrum. So here is the outline of today's talk. I'll be mainly focusing on 2 problems. The first problem is called robust quadratic sensing. And the reason I'm interested in that is because it turns out that it is a famous problem in power system called state estimation. So if I can solve this problem efficiently, then I can do state estimation reliably. So that's a big deal. The second problem is about robust reinforcement learning. And nowadays, many people are interested in applying reinforcement learning in safety critical systems. But the fundamental issue there is that reinforcement learning lacks guarantees of performance. So we are one of the first groups to study this problem and look into these directions, come up with theoretical guarantees. I will talk a little about that. So in general, this talk will be developing techniques in the areas of conic optimization, graph theory, and machine learning to address these problems. And towards the end, I'm also going to introduce some other projects in the field of trustworthy data analytics. And what is quadratic sensing? Quadratic sensing has different names in different communities, but they all refer to the following general setup. Here, I have a bunch of sensor measurements, yi, and my goal is to recover the underlying state v. The measurement equation is nonlinear. Here it is quadratic. I also know the sensing matrix mi. How can I solve this problem? Well, I can convert it into an optimization problem. That's what people usually do. Now, I just minimize this quadratic loss over the nonlinear terms, and this is known as the nonlinear least squares. But compared to classical least squares, I'm dealing with quadratic equations. And it turns out that this problem is NP hard in general. In fact, quadratic equations is a source of difficulties, and you can encode every NP-hard problem in this way. To give you some intuitions, if I look at the optimization landscape, it's quite complicated. No matter what algorithms I use, first order, second order algorithms, if I start from an arbitrary point, by following the descent path, I might arrive at a solution that is very different from the global optimum, and we call it spurious solution. And that's an issue of nonlinearity. And on top of that, we are also dealing with untrusted data. And now, if I just solve this optimization problem directly, I'm going to fail. The solution that I get will be very different from the ground truth. So this is a pretty general setup. And in fact, by specifying what is the matrix MI, you can have different problems studied in different communities. For example, in machine learning, people have been interested in matrix completion or robust PCA, where MI is a random matrix with only one non-zero element at a random location. The famous example is the Netflix challenge that I'm sure many of you have heard of. And if you specify MI to be a rank 1 matrix, then you get this problem of phase retrieval studied in signal processing, and it has applications in optics and imaging. But in this talk, I'm not going to talk about Netflix or phase retrievals, because these are well-studied problems in these communities. Instead, I'm going to focus on the case where MI has an underlying structure that is a sparsity pattern induced by a graph. And to give you an example, here is a graph with 10 nodes. And from the topology of the graph, I could get the adjacency matrix. And that's the sparsity pattern that I'm talking about. For example, node 2 and 4 is connected by an edge. And that means that if I look at the corresponding elements on the second row and fourth column of MI, it could be a non-zero pattern. But if node 1 and 9, because it's not connected, if I look at the first row and the ninth column, it's always going to be 0. So MI has a lot of zeros, and the non-zero locations is induced by the graph topology. And the question that we are looking at is, in general, real-world graphs and real-world systems often have these kind of sparsity patterns because it naturally arises from the design. Otherwise, the system would be too complex to build. Can we leverage this underlying structure to design computationally efficient and robust algorithms? Turns out that there is a famous problem in power that is a special case of it. Is called state estimation. Here, we have a power grid that also has an underlying graph structure. That is a transmission network where electricity flows. So I have a bunch of sensors at different locations. And as a system operator, I want to infer the operating state of the power grid using these sensor measurements. The sensor measurements are quadratic because of physics. So now I collect all the data from the sensors, push them to the state estimator, and the state estimator now solves this quadratic sensing problems, and the result of which will be used in a number of decision support systems like optimal power flow, contingency analysis. Optimal power flow is dealing with real-time electricity market, and contingency analysis is to make sure that the system never fails. So this is a very important problem in power. To give you an example, the picture that I'm showing you is about people streaming out of New York during the 2003 blackout, which caused serious chaos in the society and tremendous economic loss. And during the investigation of the event, it turns out that one of the key phases is that state estimation actually went out at the very beginning of the cascade of failures. And because of that, it leads to a lack of situational awareness as the event unfolds and eventually cause the blackout. So towards the end of the report, there are several recommendations, and all of them point to the direction of improving the reliability of our technologies and state estimation algorithms. So this is a problem of real consequence. What do people do in industry or in the scientific community? A lot of people in the industry would go with the simplistic models based on linearization because linear equations are much easier to deal with compared to quadratic equations. But there is a problem with mismatch. And that could be a real issue when it comes to cybersecurity because it creates vulnerability for the attacker to exploit. Now, maybe I could go with heuristics and just do a local search on the nonlinear least square problems. That's also what some people in the industry do. But because the problem is non-convex, I no longer get guarantees of optimality or bad data detection. And you may say, there are some recent literatures in the machine learning also studying gradient descent algorithms. Maybe we can use ideas there. But it turns out that the problems that are studied are very different from the one that we are considering in the real world. For example, the condition that they get for the optimality condition guarantee is based on a property called RIP, which is restricted isometry property. But we have, but will that be satisfied in real world power systems? For example, in our group at Berkeley, we have several studies saying that it really doesn't make sense to power systems, and these conditions wouldn't be satisfied. And also the bad data detection guarantees are also hard to verify in practice. There is another family of methods called convex relaxation, which is closest to the one that I'm going to talk about, but their method don't have guarantees on bad data detection. So hopefully this could situate the talk into the larger landscape. And I'm going to talk about our proposed two-stage estimation that can solve this problem to global optimality and also detect bad data with guarantees. And one condition that I haven't mentioned is called partial recovery. It turns out that none of the existing methods could achieve this. And I will tell you in a minute what do I mean by that. So when it comes to bad data, we are considering two scenarios. In the first scenario, sensors could go on or off or have faults. So we call this uncoordinated fault. For example, in this case, the sensors at location 2, 3, and 5 are fault. And because of that, we have bad data at these locations. We could be potentially arbitrarily bad values. As a system operator, the goal is to recover the true state of the system. So we want to have a full recovery. But maybe it could be the case that there is a cyber attack on the system. On a small region of the network, all the data are lost. In that case, it is impossible for data analytics to say anything of the states within the attacked region. So full recovery is no longer realistic. So maybe we need to have a compromise. And the compromise that we make here is that we want to have partial recovery. So even though we couldn't recover the states within the attacked region, maybe we can recover the rest of the states accurately. And this partial recovery is something that previous methods haven't been considered. There are no theoretical guarantees. So on the high level, I'm going to propose a method, and it goes like this. First, I will formulate a non-convex optimization problem. But instead of solving this problem in one shot, I'm going to solve a two-stage optimization problem where each stage is convex. So the optimization that we are considering here is a minimization over the Huber's laws of the nonlinear terms. Now, I use Huber's laws because I want to have robustness. Huber's laws is quadratic in the bottom and linear elsewhere. The transition from quadratic to linear is controlled by this parameter lambda. And as you can see, even though it is different from quadratic, it is still convex. So the real difficulty is in the nonlinear term. So to deal with the nonlinear terms, I can replace VV transpose with a matrix W in a much higher dimensional space. That's called the lifting technique. And of course, now I need to impose additional constraints on W to be positive semi-definite and rank 1. So I push all the non-convexity into the rank constraint. But I don't want to deal with the rank constraint. So I simply drop it. That's the standard convex relaxation technique. And now I get an optimization that is a matrix optimization, and it is also convex. I can further relax it to second order Cohn programming or quadratic programming for practical reasons like computational efficiency. And here is a key insight, and that is we are dealing with real world systems that have an underlying sparse graph. Because of that, a lot of the entries in W are not going to matter. So if you only take those that do matter, then I form a linear basis, and I can represent the measurements as a linear function. So this X is the linear basis that consists of the diagonal entries of W that correspond to the nodes of the graph, and also the off-diagonal entries that correspond to the edges of the graph. So now I get this matrix optimization based on X, but X is in a much higher dimensional space, and the elements become highly interactive. So there is a hidden infrastructure, structure linked through the original variable V. So once I get X, I need to recover V. So I need to do a second stage optimization, that is a quadratic programming. So I fill the corresponding entries of W by the estimate of X. And for the voltage magnitude, I'm taking the square root of the diagonal entries of W. And for the phases, I'm solving a quadratic programming where the parameters are based on simple trigonometric identities. So you see, this method is pretty general, and it can be applied to a range of problems sitting on a sparse graph with polynomial measurements. And in order for this method to work, I need to satisfy some conditions. The first condition is called the lower eigenvalue condition. It basically says that I have enough good data to identify the underlying state uniquely and also rectify the influence of the bad data. In fact, this is not a stringent condition, and we have tested this for a range of IEEE benchmark systems up to 3,000 nodes. And what we found is that with the right set of measurements, we can only need 3 sensors for every bus. So to give you some context, there is a famous problem in power called power flow analysis, which is known to be NP-hard in general. In that setting, there are 2 sensors for every bus. So with only 1 more sensor for every node of the graph, I can get very good guarantees of global optimality. Now, the second condition is called mutual incoherence, which basically measures the correlation between good data and bad data. The name comes from the compressed sensing literature, but the condition is very different. To give you some intuitions, here I have 2 scenarios. In the first scenario, the bad data are very different from the good data. So they actually stands out. And that makes the problem much easier. For the second scenario, the bad data are kind of mixed up with the good data, and that becomes hard to detect. In the first scenario, the mutual incoherence is a small number. Compared to the second scenario, the mutual incoherence is a large number. So if I satisfy these conditions, then I can prove a number of results for bad data. So Huber's laws is a pretty old technique in robust statistics, but we come up with some new analysis. And the result is as follows. With proper choice of lambda that controls the transition from quadratic to linear, I can have the following property. The first one is that if for all the bad data that it detect, those are all real bad data. In other words, I don't blame the good data. So this is called no false inclusion. And the second property is saying that for all those bad data with a magnitude larger than a threshold, they will always be detected. And third one is simply some bounds on the state estimation error. So if you give me a long list of measurements and a part of the measurements are completely wrong, I don't know the combination, this theorem says that I can always detect those bad data. And we also test them in the real world system. Here is a European grid with about 3,000 nodes. And we just run this on a personal computer using standard convex optimization package, and I can finish the computation within 30 seconds. And the plot is showing you the state estimation arrows. The bluer, the better. On the x-axis, I vary the number of bad data. On the y-axis, I vary the level of dense noise. You see that up to 1,000 equations could be completely wrong, and that amounts to 5% of the total measurements, I could still get a good estimate of the state. So this idea seems plausible. And then we say, okay, so the method really works in normal situations where you have bad data, but those are uncoordinated fault. In the worst case, what if there is a cyber attack? What if we have a coordinated attack? So here is an infamous example from the Ukraine power grid, but it was only after the blackout during the investigation that it was found there was a cyber attack. So if this happens to the real world systems, how secure is the system? So for the next part, I'm going to talk about robustness against coordinated attack. And for that, I'm going to introduce a new notion. For each line, I have two definitions. One is the vulnerable line. So if the attack happens, and by attacking this part of the network, the attacker would hope that due to miscalculation, the arrow would be propagating throughout the grid. So even though they only changed the data inside a small region, in this case, bus 1 and 2, because of the attack, it could happen that the state estimation at bus 4 is also wrong. And if this happens, we call this line a vulnerable line. But maybe the system operator has a better algorithm to do state estimation. And if even though the data in this region 1 and 2 are completely wrong and state estimation is completely off, it could still happen that we can recover the rest of the states accurately. And if this is the case, which is ideal, then we call this a robust line. In order to quantify robust line and vulnerable line, we propose a set of mathematical conditions. And just one thing to note is that the thing that we differentiate a vulnerable line with a robust line is not from physics, it's from the computational property of the algorithm. So the condition that we propose to distinguish these two different lines is called graphical mutual incoherence. It's basically a vulnerability index for every line of the network. Now, depending on what type of conic optimization you are solving for the first stage, it could be QP, it could be SOCP, and I have two different conditions for graphical mutual incoherence. And that leads to a new defense mechanism that we call boundary defense. So if you think about this case that part of the region are under attack, we can define the attacked region, which are marked red, and the region that are immediately surrounding that region, we call it inner boundary, and then we can define the outer boundary and the safe regions. And our theorem says that no matter how bad the state estimation is within the attacked region, if all the lines on the boundary are robust lines, then you can recover the rest of the states accurately. In other words, we can achieve local recovery using this mechanism. So this is completely new, and it also works in practice. Here is a simple example that we use real data from ERCOT, which is the grid operation in Texas. So on the first plot, I'm showing you part of the buses are under attack. Maybe some hacker hacked into the system and then changed arbitrarily the data about these regions. So the attacker would hope that it would create a chaos for the rest of the grids, and indeed, this is what will happen if you use current industry's algorithm. You see all the states estimation are completely off because of the local attack. But if we use our proposed method, and we also check the graphical mutual incoherence conditions on the boundaries, they're all satisfied, we actually have an effective boundary defense. All the errors are contained within the boundary. So using this new mathematics, we can actually evaluate the entire US grid. Here, I'm showing you the topological distributions of robust lines, which are marked green, and vulnerable lines, which are marked red. In general, there are 59% of lines that are robust, which is not a bad number. And you could also see the kind of topological distributions of the robust lines versus the vulnerable lines. But what's even more exciting is that because of this new mathematics, we now could build exponential number of certificates of defense against cyber attacks. For example, you could think of a region that you want to attack the system, say New York, and if you could draw a circle around that region, and you can check all the graphical mutual incoherence conditions. If they are satisfied, then you get a certificate of defense. So in this way, we can get millions of attacks and defense scenarios. And this is never done before because previous method is only one condition for one attack scenario. And most importantly, I can evaluate this metric very efficiently. In fact, I can evaluate the entire US grid on a personal computer within a day. So that's really powerful. And you could imagine using this new mathematics to do more things. For instance, you can define a critical index for each bus of the system that calculates how many neighbors would be affected if this particular bus is under attack. So we assign a number for each bus in the system. In general, this plot is showing you the critical index for buses with values more than equal more than 2. So it's not a lot of vulnerable locations, and the highest number is 3. So it's not particularly bad, but it also happens at populated areas like New Jersey and Delaware, so that might raise an alarm. And of course, we could study the optimization properties. As I mentioned, in the first stage, you have choices of either doing QP or SOCP. And our analysis is saying that the incorporation of the SOCP constraint will always improve the robustness. So on the first plot, I'm showing the vulnerable locations using QP. And compared to the red plot where I use SOCP, you see that after incorporating the second order cone constraints, I can improve the robustness of the system. And of course, I could extend this technique from a single line to a box of lines using a tree, using a classical notion in graph theory called tree width. Tree width is has different names in different communities, but they all refer to the same thing. That is the boundary between easy and hard problems. And what our result found is that, for example, for the European grid, it has thousands of nodes, but tree width is bounded by number 35. New York grid is smaller, but it's more congested. The tree width is bounded by 40. And we can use this notion to extend our definition from a line to a box of lines to define the graphical mutual incoherence. And the result is that we will be able to improve the robustness guarantees. So in the first part, I sort of talk about our defense mechanisms against both uncoordinated fault and coordinated attack. But I sort of waved my hands saying that the attacker could always design an attack strategy. But in reality, the attacker will be constrained in resources. More specifically, the number of bad data they can manipulate are really limited. So in the next part, I'm just going to brief. All right, coming back to the attackability of the system, we start with this assumption of the attacker, that the attacker could access the information about the grid as well as its data, but it is constrained in the number of measurements that it can manipulate. The optimization problem is easy to formulate. The objective is that the attacker wants the system operator to believe in a state as close to a target state chosen adversarially as possible. But it needs to satisfy several conditions. The first condition is stealthiness, which means that the attacker doesn't want to be detected. And the second condition is a limit on the number of sensors that the attacker could manipulate. And once you formulate the optimization, you immediately see the challenges. The first challenge is that we are having nonlinearity as before. That results from the quadratic inequalities. And also the cardinality constraint is also difficult to deal with. So because of this, we are dealing with a non-convex problem. And just briefly, our method is to design a panelized semi-definite programming to solve it. We could start with this original optimization problem that is non-convex, and then I can convexify it to replace the VV transpose with the matrix W in a much higher dimensional space, and also replace the cardinality constraints with a penalty on the objective. I can drop the rank constraint, that is standard SDP relaxation, and now I arrive at a matrix complete problem that is convex. But there is a twist. And the twist is that if I solve this problem directly, the solution is not going to be rank 1. And that means that if I recover the solution, it's not going to be feasible for the original problem. So the information that we get will be completely meaningless. So to give you some geometric insight, the blue region is showing you the feasibility set of the SDP. And if I approach this from a wrong direction, then I might get a solution that is high rank and that is meaningless. And many people would just say, okay, maybe the problem is too difficult because it's NP hard in general, we just give up. But our idea is saying that maybe we can change the direction of the objective so that it approaches this feasibility set in the right direction so that we get a rank 1 solution. And in order to do that, we need to add a penalty to the objective. Now, the form of the penalty is pretty general. I got to choose what is the penalty matrix I'm paying here. So you could, if you are familiar with the compressed sensing literatures, people use nuclear norm, which correspond to the case where M penalty is the identity matrix. But here in power systems, if you use nuclear norm, then you are penalizing the voltage magnitudes, which are strictly controlled by the system operator. So it doesn't make sense. So instead, we need to design our own penalty accordingly. And our theorem says that we are able to come up with a penalty matrix so that once we solve this SDP problem, we can get an optimal solution that is unique and rank 1. Now, I should take a step back and say that the original problem is NP hard in general. And the reason that we can come up with this penalty is because we can exploit the optimization properties of the original system. Now, for different optimization, you might need to come up with different strategies. So this is not a silver bullet, but at least we could prove that we can get a rank 1 solution after using this penalty approach. And we are also able to prove a number of bounds on the bad data, but I'm not going to the details. So that sort of concludes the first part, where I deal with quadratic sensing problems that are NP hard in general, and I design an algorithm that is computationally efficient. And for the second part, I'm going to talk about robust reinforcement learning, because many people are interested in using reinforcement learning in the real world systems. But the problem is that once I want to get some theoretical conditions for reinforcement learning, I immediately see several challenges. The first challenge is that the original system is nonlinear, and also the neural network policy is nonlinear. And the policy is also changing over time. So because of that, analyzing the stability condition will be quite difficult. So here is a general setup of the problem that we are considering. We have a linear part of the original system together with a nonlinear part. The nonlinear part could be quite general, could be time varying, or could be uncertain. And for the controller, we use a neural network. And our theorem says that we could delineate a set of safety controllers so that as long as the policy remains within the safety set, then we can certify the stability of the interconnected system. Now, to calculate this safety set, we need to solve an SDP problem. And the intuition of that is if you consider you are driving on the road, when the scene changes, your wheel shouldn't change that much. That's why we look at the input-output gradients. And the SDP that we're going to solve is based on the original system that has a linear part together with uncertainty on the a constraint on the uncertainty part. And once we solve this SDP, formulate this SDP problem, we can either certify the stability or not, depending on the feasibility of this problem. And we test this in a real power grid. Here is a nonlinear model, and we also have information constraints. So these generators could communicate with each other in order to control the frequency of the grid. And the result is saying that if you just leave the reinforcement learning running on their own without any constraint, at some point, as this blue curve shows, you are going to destabilize the system, and that's what we don't want. But if you use our simple strategies, you could keep improving without destabilizing the system. And that is a key step towards incorporating AI into the safety critical system. Now, in the last part, I'm just going at high level about some projects that we have been doing in this realm of trustworthy data analytics. The first part is about computation, where I develop techniques in the general framework of safe and reliable learning and control. The first issue is about sensing. Right now people are treating sensing as silos with the rest of algorithms, but maybe we should integrate that into the pipelines. For example, in this video, I'm showing a robot kind of navigating the space in order to find the pollution sources using reinforcement learning. And it's not just about active learning. It's really about incorporating the physics and navigation capabilities and real-time decision-making into this cyber-physical system. And the second part is about data-efficient learning. I sort of talk about robust learning. When it comes to generalizability, we also need to deal with insufficient data. So we have worked on a bunch of techniques that incorporate the physics and prior knowledge into the system to deal with this issue. For example, I have used the prior knowledge and to create a number of artificial labels to train the algorithms, and that matches the performance of algorithm trained with full data. That's also called a weak supervision. And the second direction is to incorporate the physics into our learning to deal with data efficiently. And also, we see a lot of systems have graphs and data sitting on top of it, but graph learning has issues with vulnerability. Essentially, you could attack the topology of the graph by adding or deleting edges, and that completely changes the output. So we have worked on a new methodology that can improve the robustness of graph learning algorithms and can have a simultaneous improvement in both the clean data and adversarial data accuracy. The second part is about human interactive learning and control. And I think the key there is to develop mutual understandings between people and systems. For example, I have worked on the problem of inverse reinforcement learning, where the goal is to infer people's intent based on their behaviors. Now, the challenge is that we need to deal with limited data and also the complexity of the human mind. So we propose to use deep Gaussian process as a way to model this, and we solve that and demonstrate it to learn about people's driving behaviors in the low data regime. And another direction I think is interesting is how can we nudge people in the right direction for social benefits. So we have worked on a project of gamification where we engage people in a game setting, we collect data about them and learn about their behaviors in order to design the optimal incentives. We demonstrated in the real world settings where we can achieve energy saving of about 30% in a small office at Berkeley. And now we scale this up to a large dormitory with about 100 students in Singapore. So in order to have an impact, I think it is important to work with domain experts. For example, my work on human-centric sensing has been deployed in various locations in Singapore to manage the indoor environment. And I have also been working with Lawrence Berkeley Lab to develop and deploy the computational tool for microgrid design in several cities in China. And right now I'm working with Lawrence Berkeley Lab to develop the trustworthy and robust reinforcement learning for building controls. And the exciting part is that we are going to have real demonstrations. And I've also been working with Carnegie Mellon universities to kind of incorporate AI technologies into the real world settings, into the deep space explorations. And the motto there is that we want to keep people alive when they are inside the space habitat, but also keep the habitat running when people are not there. So just to conclude this talk, I have talked about two different problems and also the aspects of trustworthy data analytics. And a lot of that is about optimization. For the first part, optimization, the bottleneck is the quadratic equations, so we come up with techniques to address it. And for the second part, we propose some method to certify reinforcement learning. And perhaps the big message that I want you to take home is that optimization in its general form, especially non-convex optimization, could be really hard. But because we are dealing with real-world systems, often there are structures that we could incorporate into our learning or algorithms that make it more efficient and also can help us get better robustness guarantees. And so with that, I would like to conclude the talk and thank you all for your time and thank my collaborators. Without them, these works wouldn't be possible. Yeah.
Thank you so much, Ming, for your presentation. We have some time for questions, and to ask questions, I would recommend you say your name and your institution, and then ask your questions. So yeah, go on, if anybody has questions. If not, then I'll ask a question to Ming. So most of your research that you have told about trustworthy data analytics mostly are from the power system point of view or smart building point of view, right? So and many of our researchers in the computer sustainability area have a wide range of topics like wildlife and water and all the other natural resources. And also, do you think all these areas can be, all this knowledge that we gain from trustworthy data analytics can be transferred to all different areas? Is there a generalizability of these methods that you are trying to develop?
Sure, I think we are in this field of computational sustainability. We have worked on a variety of important problems like wildlife, like how we can design the urban systems. These are all very important problems. But the underlying methodology is that we want to have, for example, information about the systems, and we want to get actions based on these informations. And in a lot of these cases, I would argue that you could make it into an optimization problem. Well, the optimization problem itself might be hard to formulate, and that itself could be a challenge. And once you formulate that, you need to also deal with a lot of issues like unreliable data, untrustworthy, like nonlinear systems, and a lot of these issues. So the method that I'm talking here is in the general case, how we can formulate optimization and solve it efficiently. And the message that I want to deliver in this talk is that, when you look at your optimizations, instead of just treating it as a data in, decision out systems, you should try to look at what are some underlying structures that you could exploit in your systems. For example, if you are working on transportation, transportation itself has underlying networks. So by exploring the networks, we could actually design much more computationally efficient algorithms. And it's the real world properties that are often making these optimization problems easier to solve. So instead of just like saying the problem is too hard or we just satisfied with finding the local optimum, maybe there is hope to find the global optimum and get a much more reliable information out of the data.
I see. Thank you so much, Ming. Does anybody else have any questions? We have time for 1 or 2 questions, maybe. I don't see anybody has a question. So thank you so much, everybody, for attending this talk. And our next meeting will be on 21st February, the same time. And the speaker will be Amrita Gupta from Georgia Tech. And thank you so much. Thank you so much, everyone.